Right. Now let's begin now to look at electrochemistry. Okay. So we begin to look by the thermodynamics of electrochemistry. So we'll start with an introduction on. So what are the objectives of this lecture? I'd like you to appreciate, as I said, the basics of electrochemistry. Then I also like you to appreciate presentation of important electrochemical and thermodynamic data um, using Paul diagrams. And then I also want to understand the application of Paul diagrams in hydrometallurgy. I'm going to delve much on these issues of thermodynamics of electrochemistry. Okay, right. So the chemistry of hydrometallurgy is mainly based on leaching and recovery. Of course, there's an important step between them. Okay, but what I need you to understand is that the leaching and the recovery are different, two opposite processes. Whereby you're leaching, you're moving from your solid into aqueous state, and then for your recovery, you're moving from aqueous state back into solid state. Okay, so those are the two things that you need to understand about the chemistry of hydrometallurgy. It's simply a mass transfer from solid to aqueous when you're talking of leaching, and also a mass transfer from aqueous to solid when you're talking of metal recovery. Now, the basis of these reactions is basically two types of reactions that are involved. Okay, so the first one is your acid-base reaction. Okay, so either you're doing leaching or your metal recovery, you'll probably be doing acid-base reaction. So what is an acid-base reaction? Acid-base reaction is one that involves a proton exchange. Okay, there is a proton exchange, and maybe in also times it might be a hydroxide exchange or formation. But your acid-base reaction is generally occurs when there is a proton exchange. And then there is also the second part here of the chemistry of hydrometallurgy, which is an electron exchange. Now, if there is an electron exchange, this is now termed as your redox reaction. So these two types of reactions are the important basics of the chemistry that is happening behind every leaching or every recovery process. Is either your acid-base reaction or your redox reaction, as we have depicted here. Okay, right. Now consider the deposition of a metallic element, let's say X, and then we are using the reaction of this metal X 2 plus, and you are doing its reduction using hydrogen gas, as shown in the reaction below here. So we can see that your X2 plus metal, okay, something is happening, okay, and then here there's some electrons that it uses, because it's coming from an aqueous state into a solid. It's being reduced to form a solid state. So here there is an electron usage here, and what's happening to hydrogen? The hydrogen, as it forms hydrogen ions, it's actually releasing these electrons, and then these electrons are the ones that are now being used by the metal element for it to be reduced from aqueous state into solid state. Okay, so we can see that the electron donor, which is your H2 gas here, it's a reductant, and then your electron acceptor, in this case your metal ions, is the oxidant in this case. Okay, so we can see that the deposition in this case now, it is involving the transfer of electrons from the hydrogen gas to the metal ion. Okay, so reactions that involve electron transfer are actually oxidation or reduction reactions, simply put as redox reactions. Okay, as we have said before. Okay, right. So What are some of the reactions that are important in hydrometallurgy? Okay, so this is an example. For example, your metal here, dissolution of your metal from solid into aqueous state here. This is a simple redox reaction here. Okay, then you've got your metal oxides and metal hydroxides also. Okay, this is your metal oxide being leached probably in acidic conditions, and then it forms a metal in aqueous state. So this is an acid-base reaction because of the presence of the protons here. Then you can also have your, which is the same, your metal hydroxide here, in this case, also being leached probably in acidic state, 2H plus, as we can see. And because this is a proton, it is also an acid-base reaction. Then you've got your sulfides as well. They can be also leached. So in this case, you can see your metal sulfides also being processed in acidic conditions. So this is also an acid-base reaction because of the presence of protons. Okay. Then here we can see your metal sulfide here breaking down to M2 plus, and then there is a release of electrons. So simply, if there is electron transfer, it's simply a redox reaction. Okay. And then also here we have also, it is also your redox reaction with the presence of electron transfer. Okay. So as we said, we are moving from your solid into aqueous state and then into solid state. This is now a pure metal. Okay. So the concentration of metal ions in solution is a very important aspect when you are now talking of thermodynamic chemistry. But you realize that instead of using concentration, we use the term activity. I'd like you to find out why do we use the term activity and not the term concentration when you are now doing these thermodynamic diagrams. Why do we use activity? We prefer to use the term activity to depict the concentration of your metal ions maybe in solution. Okay, so the activity, when we look now, for example, we have got this reaction here. Okay, then we introduce logs. You can see that we introduce log to this equation. So you can see that log activity of the metal ions is equals to minus log K minus log minus 2 pH, which is the log of your concentration, the log of your activity of your hydrogen ions. So when you put the log of activity and then the log of a pH on your x-axis as shown in this diagram, in this log activity diagram for your acid-base reactions, this one is specifically for your metal hydroxide precipitation. This gives you an indication and it gives you a starting point, an idea of what to expect when you're doing, for example, you want to do your metal hydroxide precipitation. Okay, then you want to conduct maybe what is called sequential extraction or sequential extraction using precipitation. So you can see that if you, for example, if you want to start from a low pH and want to raise your pH, you can see that the first elements that you are, for example, let's look at log activity maybe around 5 here. So you're going to realize that you're first going to precipitate out your iron, maybe then your tin, and then your aluminium, then your lead as you go on, as you increase the pH. This is how you use these log activity diagrams to give you a starting point. Okay, in terms of pH, it gives you the conditions or the stability points of certain elements or certain in this case your precipitates. Okay, so these diagrams are very important as a starting point, and as a metallurgist, when you're designing a process flow sheet, you are supposed to understand the thermodynamics that is involved in the log activity and in the pH, when you compare the pH and log activity of these reactions. Okay, so let's look at another one. So this is now the log activity of your metal sulfide precipitation. Okay, So assume here you've got your this is the reaction of your metal sulfide, okay? Then log activity of your metal ions in solution is given by this formula, okay? I'm sure you now know what your K is, okay? So we can also see here, as you move from the left to the right, you can also see that your copper sulfide will be actually the first element to precipitate, followed by your cadmium sulfide. So assume that you want to precipitate out sulfides from an aqueous solution, and you've got your copper, and you've got your cobalt, and you've got your iron. You design your process such that you move first your copper, then maybe your second you go to your cobalt, and maybe your third you precipitate out the iron. Okay, so you want a sequential extraction, you want sequential precipitation so that you collect these precipitates at different stages and separately. Okay, so this is the importance of these log activity diagrams for a metallurgist when you're designing a process. This is your first port of call when you're trying to design a process. So there are many other conditions that you can now actually introduce, but in this case, you are simply comparing the pH, the stability regions in terms of your pH and in terms of the activity of your metal ions in solution. That's how you are now defining, in this case, your precipitation of sulfides. So you can have different precipitants. The previous one we're precipitating out as a hydroxide. Now we are precipitating out as a sulfide. Okay, right? So now, well, let's look at another example. So this is your log activity diagram for metal oxide leaching. Okay, so in this case, again, let's assume this is your metal oxide leaching reaction. Your metal oxide being leached in acidic conditions, and then it goes into aqueous solutions, and water is produced. So again, assuming you've got a complex ore that has got different types of coexisting mineral elements. Using this diagram, you can have an idea of what to you can have an idea of which elements precipitate or which elements are leached out first or last, because in terms when you are comparing in terms of your pH. So you can see this line here, for example, this line here. In this line here, we can see that when you are above a pH, let's just say above a pH of 1.5 etc., then your Fe2 plus is actually more stable. But below this pH, your Fe3 plus becomes more stable. So this is the region where you can now be able to leach your Fe3 plus, okay? Because above it, it precipitates out. Instead of leaching, you are now precipitating your Fe2 plus. Okay, so for your sequential leaching, sequential extraction, again, you can say, or if you start in acidic regions, you can actually leach out all these Fe3 plus ions, and then if you increase your pH, let's say you've increased your pH to around 5 here, the next so in all this region again, you can actually extract out your aluminium also, because Al2O3 plus becomes stable at this line. So here your Al3 plus is actually stable, so it means that you can leach out your aluminium. Okay, then again, if you increase your pH, okay, you can see that here above this line, your zinc is stable as ZNO, as an oxide. So here, before here, you can actually leach out all these conditions can be able to leach out your zinc. Okay, so depending on what the structure of your element, the structure of the composition of your ore, you can actually be able to do some sequential extraction or sequential leaching, so that you remove whatever, so that you leach your metal of choice all reach a certain element, first of all reach a certain element, first of all reach a certain element, and then you move on to them to the next. So in this case, we have seen the stable regions and the stable where the stable phases of different types of your oxide and the metal ions are in stability. So using that, you can now design your process, knowing that this is where maybe I'll start by leaching out my zinc, and then maybe I'll leach out my aluminium, and lastly my Fe2, based on the pH, based on the pH. So this is very important when you're doing, especially designing a process flow sheet for an ore which has got different types of composition. Okay. Now, so let's look at electrochemistry. Now, let's begin to look at electrochemistry. As we have seen the importance of the activity, the importance of some thermodynamics data, let's now begin to look at some electrochemical studies. So what is electrochemistry? It's generally a phenomena of studying your electrified interfaces. Okay, so there is electron transfer, okay, and then there is an electron conducting substance, okay, and the phase conducting ions. Okay, so that's your that's basically what happens in electrochemistry. There is electron transfer that occurs over a certain interface between your electron conducting substance and a phase conducting ions. Okay, that's your electrolyte. Okay, right. What are the elements of an electrochemical system? So you need to have an electrode, you need to have an electrolyte, and possibly a membrane, okay, a permeable membrane. Those are the basic elements of an electrochemical system, okay.